The world's biggest Jacob's ladder. This is the new record holder for the world's biggest Jacob's ladder. This video clip was captured at the 500 kilovolt El Dorado substation near Boulder City, Nevada by power company engineers and maintenance staff. It shows a three-phase air disconnect switcher attempting to open a high voltage supply to a large three-phase shunt line reactor. The line reactor is a huge transformer-like object behind the truck at the far right at the end of the clip. Line reactors are large iron core coils which are used to compensate for the effects of line capacitance on long extra high voltage transmission lines. Internally, each phase of the reactor is connected through a large coil to ground. Each phase within the reactor is capable of providing 33.3 million volt amperes of inductive reactance at 290 kilovolts between each phase to ground. The power company was having difficulty cleanly disconnecting one phase of the line reactor and had to set up a special test to videotape a switching event so that they could diagnose the problem. The engineers had also made arrangements to kill the experiment by manually tripping an upstream circuit breaker. This particular switcher uses gas-filled switching elements called gas puffer interrupters. These are located just to the right of the rotary air brake switches. The interrupters' switching elements are housed within sealed bottles filled with a special insulating gas under high pressure. SF6 helps to rapidly extinguish the arc that's created whenever a high voltage circuit is broken. During normal operation, the switch will first open the SF6 interrupters. This disconnects the HV circuit so that the air breaker switches can open with no current flowing. Once the air brake switches completely rotate to the open position, the SF6 interrupters then reclose. The actual SF6 interrupter switching elements are hidden inside the grey horizontal insulators. These particular interrupters use two SF6 bottles that are electrically connected in series. It takes two switches in series to share the high voltage stress. A single switch can't handle the voltage. In this video, one of the pairs of the FF6 interrupters is defective and it fails to open. This places the entire voltage stress across the remaining good interrupter. As the good one valiantly tries to open the inductive load, it creates a high voltage surge that causes the bushing of the good interrupter to flash over. The initial flashover can easily be seen at the very beginning of the video clip. Since the affected phase remains energized through the conductive flashover arc, the air brake switch begins to open hot, still energized. It continues arcing as the switch rotates 90 degrees to the fully open position. Once the air brake switch reaches the fully open position, the SF6 interrupters then reclose. Although this extinguishes the horizontal arc across the good interrupter's bushing, the arc across the air brake switch persists, continuing to grow and creating a very dangerous situation. The arc stretches upward, driven by rising hot gases and writhing from small air currents, until it easily exceeds 100 feet in length. Switching arcs usually terminate long before reaching this size, since they normally flash over to an adjacent phase or to ground. Once this happens, the phase-to-phase fault current will cause an upstream circuit breaker to trip, disconnecting the circuits. A phase-to-phase arc can be seen at the very end of the previous 345 kilovolt air brake switch video, just before the resulting short circuit trips an upstream oil circuit breaker. Since this 500 kilovolt arc was in open air and was sufficiently removed from adjacent phases, it could have persisted for quite some time. To avoid risking further damage to their equipment, the utility manually commanded an upstream circuit breaker to open, abruptly extinguishing the arc. After this event, it was determined that both FF6 switch bottles in the affected phase had sustained permanent damage. The bottles were sent back to the manufacturer for analysis to determine the root cause of the problem. Loss of pressurized insulating SF6 gas inside one of the interrupter bottles is suspected as the initial cause of the switching failure. As impressive as this huge arc may be, the air brake switch was really not disconnecting a real load. This arc was only carrying a relatively low, perhaps 100 amps, magnetizing current associated with the line reactor. The 94-mile transmission line associated with the above circuit normally carries over 1,000 megawatts of power between Boulder City, Nevada, from the generators at Hoover Dam, to Los Angeles, California. A brake under normal load conditions, approximately 2,000 amps, would have created a much hotter and extremely destructive arc. Imagine a fat, blindingly blue-white, 100-foot-long welding arc that vaporizes the contacts on the air brake switch and then works its way along the feeders, vaporizing them along the way. Still, you've got to admit that this little 33 Ember arc is certainly an awesome sight. And who says utility guys don't have any fun? Just listen to linemen on the right whoop at the end of the clip.